Okay. Hello, everyone. Hello.
Good morning.
Yeah, good morning. I'm good. I'm good.
Morning. I started, yeah?
Sure.
We start our presentation from geometric technology. Our presentation will consist of the three main parts. First part is the RTH introduction about theory and some else. The next part is concerning with the processing interpretation case study. And maybe it's more interested for you. And the last third part is concerned with driving machine learning and prediction case study. Okay, I just now extended our first part, and the main slides concerned with the comparison of the well-known method reverse time migration, which proposed more than 40 years ago, 3 men from USA. Reverse time migration at the left part, and RTH, reverse time holography, at the right part of this slides. Both of method take the two stage. First stage, decomposition stage. The second stage is synthesis stage. What is for the reverse time migration? Obtaining Code-Sherman gather, we decompose with using two wave second order equations for the forward and for the back is with reverse time, and decompose and obtain for each voxel obtain through two value of pressure forward, pressure back, two way. It's a data set called common image gather. For each voxel we obtain two value, space 2, and for the reverse time holography we use the first order acoustic equation, which calculate pressure forward, pressure back, and forward vector particle velocity, back vector particle velocity. Also we obtain 6 plus 2, 8 value in each velocity, in each voxel. Space 8. Space 2, space 8. Space 8 data set is more huger than common image gather, approximately 1,000 times more. What is the next stage? The next stage called applying RTM reverse time migration imaging condition, very famous imaging condition. What is imaging condition? By simply integration by source and time, by source. In our case, we obtain 8 parameter, and stage of synthesis deal with the estimation of statistical parameter of the multidimensional stochastic distribution. Multidimensional is maybe 10 dimensional plus source number time. Is differ. The vector domain coming together is more powerful data set, and for conventional reverse time migration, this applying imaging integration by source and time, we obtain one value with sign. Fine, one value with sign. This is a value of so-called RTM imaging. It's exactly coincide with the Kirchhoff migration. No different. So in each voxel we obtain obtain one value with sign, and obtain in all value we obtain the RTM reverse time imaging. In our case, in each voxel we we estimate the huge event and can obtain the direct RTM imaging, for example, RTM RTH imaging, RTH impedance, RTH fracture at velocity, and many other, more than 100 attributes. So reverse time holography vector generalization is a vector generalization of reverse time migration. First, okay, it's what is a feature of the reverse time holography with the conventional imaging method. RTH is de facto heat as a new seismic exploration method, time-dependent full scattering seismic exploration. Why? Because we use extended scattering model, not 3D space, but 4D space, 3D space plus time. So the indicators can change in space and it can change in local time. Its principle differ from the before the all this method before which use only static 3D scattering imaging, scattering indicators. So method is based on two fundamental principles: reverse time and two beam interferometry. It's two discovery of last century: reverse time and two beam interferometry, which is head of the holography. Normal. RTH uses a proprietary imaging condition based on the extension in time and using the analysis of interference of particle velocity vector of incident and scattering. So we use not amplitude as a reverse time migration, but also we search and use phase, not and amplitude and phase. Due to vector interferometry, voxel-based arbitrary construction, reverse time holography differ from other migration and velocity tomography method by high spatial resolution up to 2 meters, size of the voxel. Hyperattribute generation of 100. RTH tool is for RTH is tool for the time-dependent scattering, time-dependent model scattering. Which depend on not only space, but local time. This method is ideally compatible with well logging and testing data for purpose of geological and petrophysical prediction base. So, in our conception, total scattering conception, what is a reflection wave? Reflection wave is only in phase scattering at sharp boundary, no more. Only reflection, only in phase scattering. It's reflection. And classical diffraction, what is it? Is only weak scattering by small homogeneity is Bohr approximation. So reverse time holography is by mathematical reason cover all existing approach, all existing methods: PSTM, reverse time migration, IVO, CSPD, diffraction, migration velocity, inversion. By mathematical reason. This is example what is in some additional view what happens. Black box scheme and statistical parameter estimation. Propose we have the one voxel. There exists input signal forward, and after scattering in each voxel, we can obtain output signal. Is the angle, is time sure, and angle and the time dependent. This input, output, and our purpose to know what is petrophysical property of medium. The general purpose of the reverse time holography. It's simple. What about reverse time holography velocity model building? It's a very important part because this is attribute calculated the firstly. It's important because initial velocity model as a rule we constant we have to constant or maybe ingredient. And what process of the estimation? In each point we obtained two vector, forward vector and velocity vector. And for some time we obtain data set, some data set which we can see at the right part of the, and for each voxel, we can obtain two data set. If our initial velocity exactly coincide with the real velocity in this point, in this case we obtain the arrival to wave in zero time. If more, this some plus, delta plus, or maybe and use canal equation, we can estimate fluctuation at delta time in millisecond and estimate velocity. This is an example of the initial velocity gradient. It's with automatically we can calculate second, third step, and we obtain some characteristic of initial velocity model. This is the RTH velocity slice on some depths, very detailed, This is a testing with the RTH method on model data, which I calculated more than 10 years ago.
Sorry to interrupt. Can we just go back one slide? Yes. On the top, it says the 3D initial velocity model in inline. That is, first one is the initial, and last one is all the refinements after each iteration. Is that so?
Yes, it is initial gradient, pure gradient.
And V2, V3 up to V7, there are subsequent iterations. Is that so?
Yeah.
Okay. Thank you.
Yeah. The first our testing model concerning with reflection and diffraction. What is the reflection, diffraction? Because we operate with amplitude in phase, we can to desire some filter by amplitude, by phase, and separate only, for example, only reflection. For example, only diffraction. Select only diffraction, 2 point, all diffraction. Or maybe, for example, RTM prisma wave. We want to select RTM prisma wave. It's no problem. It's only vertical line. Yeah, it's more than 10 years ago. I done a test. Is the fundamental achievement of the RTH method, why is vector of nature, is the decomposition of the vector field in two components, back vector field in two components, the hard and soft scattering component. According to the hard, it's reflection or diffraction or scattering of the velocity of the point with more velocity, and soft with a point with low velocity. So each attributes automatically we divide for the hard attribute and hard part and soft part, soft part, using the rotation of our the phase. Hard without changing of phase, soft without 180 degree inversion of the in the point of scattering. It's, I think, it's clear. So if we use, we have two parts, we can do what is the differ, for example. What is the differ? Differ, and so we obtain in each attribute for the rambling velocity, we obtain the differ very similar to the migration, but it's not migration because we have not done migration. It's RTH velocity imaging. Why RTH velocity imaging? Because they very similar the so-called FWI imaging, which proposed 5 years ago company CGG company, we well know. And with summation, for example, so we obtain for the RTH velocity. So for each attribute. The next feature, robustness of sparse regular in irregular seismic condition. Excuse me. One more. Ах ты, ровно. One more. This feature is some outlook about optimal survey parameters, acquisition parameter about recording, optimal distance between receiver, optimal distance between source, optimal hold, and so on. This example which shows the stable concerning the sources. At the right part, we can see this 100% sources. We use 100%. About 400, I think. This is 70%. This is 50%. Half of the sources we destroy, we remove. This is 20, and this is 10%. So it seems that for this estimation, because it's stochastic estimation of multidimensional scattering, it's 50 value of the number of sources. It's enough because correctness is very similar, And then the next feature.
Professor Erokin, can I just go back?
Yeah.
I have a question. I'm a little confused. You say that optimal recording frequency is 2 to 4 kilohertz. Normally, if you're talking about seismic, even if we normally we talk about sampling interval, which corresponds to frequency. So even if we go for 1 millisecond, okay, so our frequency is 100 hertz. Now you're talking about 2 to 4 kilohertz. So what is my sampling interval? Do we really do sampling that? I mean that frequently. I'm not sure.
Optimal. It means that it's very good to use for gigahertz, but also we used for 2 milliseconds sampling.
The 2 millisecond will correspond to 250 after Nyquist.
Yeah.
So it'll be much less.
2 milliseconds.
Mm-hmm.
2 milliseconds is enough.
Okay, and over here, you can explain it a little further. It says, what are the panels, the 5 panels that I'm looking at? What is the color coding? It says, can you just explain it a little bit?
What is, excuse me?
On the right side, there is a panel of 5. You say the optimal survey, this 10% to 100%.
This is one of attribute RTH diffraction. RTH diffraction for different. One of the attribute is
what is the color? What is the color code?
Much red is maximum of the diffraction. It's correlation with the fraction, for example.
Correlation with fractures, you say?
Yeah. Diffraction.
Okay. Okay, correlation diffraction. Okay, so so the maximum is the maximum correlation of diffraction. Okay.
Yeah.
Thank you, sir. Please go ahead.
The next, maybe last feature of the reverse typography is high super resolution. What does it mean? This is not concerning with relay super resolution about lambda divided of 2 or 4. It's concerning this with using interferometry. When we use interferometry, we can, using phase, we achieve super resolution. For example, for modeling 1D diffractor source with velocity wavelength 50 meter, flickers 40 kilohertz, and velocity 2000 meter per second. Distance is the right two diffraction. 2-point diffractivity with distance between 2 point 1 meter. 1 meter. This is 1 meter, and we can see the differ backscattering at this point. So our super resolution 1 meter, 2 meter concerning not amplitude but concerning the phase, exactly phase. As similar for the interferometry in physics, very similar. Okay, Nicolette, excuse me. Two participants. Okay. Excuse me, all of participants, because we starting maybe.
Hi, Nicolette. We started earlier because we had some participants.
Because some mistake we concerning the Mexican 10.
It was misunderstanding, but we have everything recorded, so we're gonna share the recording.
I can repeat to the starting with this first part of introduction. So is to-beam migration method according to mathematical wave model. If you use pressure at this point concerning as a pre-stack time migration, depth migration, is I call this pressure-based seismic. Is use vector to vector, as in our case. This is scalar vectors based seismic. And if you have in elastic, we use tensor to tensor forward and back tensor. It's tensor based seismic. This is picture concerning the perspective concerning the pressure, vector, and tensor. And the last part of the some conclusion of the introduction. First, RTH properties. New 4D extended scattering model concerning. 4D backscattering model used in RTH assumes that scattering can depend not only one direction, angular anisotropy, but also on the frequency or local time. First, concerning ultra-high resolution. The principle of two-beam interferometry and time reversal of seismic waves significantly increase the spatial resolution, which is limited only by voxel size. Only by, for example, 2 meter is limited for voxel size. Its resolution will be 2 meter. Hyperattributivity. RTH generates more than 100 independent seismic attributes per voxel. Intrinsic automatic velocity estimation is feature of the RTH. High resolution up to meter velocity model. And the next, I already depth domain output directly compatible with the well-log and machine learning. And last, robust or to sparse and regular acquisition can reduce field survey and cost by 2-3 times. So, finished. RTH in new paradigm, I said it's a new paradigm, I think, of 21st century, so-called time-dependent full scattering seismic exploration. I call this time dependent, full scattering, no reflection, no reflection. This reflection only in phase scattering case of our full scattering seismic model. So the next part concerned with the processing interpretation. Very similar, but conventional, but it's different. Some there exists different. First slide concerning the benchmark RTM RTH for fractured basement. Very important fractured basement is line. This is line thin plate is target horizon, and this is fracture is basement, fracture basement. This is reverse time migration, very similar Kirchhoff migration depth. Is one of our attributes called RTH phase. More detail. This is RTH velocity. Green thing concerning the low velocity and deal with the fracturing. With the fraction, this is fault. This is fault. The next very similar, but this is we use diffraction, RTH diffractivity, Kirchhoff migration, RTH phase, and our velocity. The same upper fraction. Very interesting, very approach. This is an example of our 10 years ago. We firstly obtained this is comparison of the pre-stack time migration. What is pre-stack time migration? It's high velocity. It's what is the image of the our velocity, RTH velocity. This is similar comparison of pre-stack depth migration as the down left with the RTH velocity upper and down right so-called RTH velocity imaging, which I mentioned with similar missing by the design and by result, by resolution, very similar for because this obtained from the velocity software hub is RTH very similar to RTH full wave FWY imaging, so-called. It's not migration. It's not immigration. Only this is imaging we desire from the velocity. This is a comparison of pre-stack depth migration at the left, RTH velocity, similar to the migration, but not migration. And this is at the right, it is RTH velocity fluctuation. So at the depth migration, we can see only low, only higher fluctuation of velocity. This is and this is, and on the our RTH velocity imaging, we can see also the high fluctuation velocity and low fluctuation velocity, high or low. This is a zoom of pre-stack depth migration RTH velocity. Pre-stack depth RTH imaging. This comparison of RTH velocity and with RTH velocity imaging and diffractivity for 25 kilometers. This zooming, this left zooming is RTH imaging, is diffractivity. This to diffractivity and RTH velocity imaging weakly overlapping. Red color is diffractivity concerning the fracturing, and overlapping is RTH velocity imaging. Is zoom. This is similar for upper part of the depth section, 500 meters. This is natural fracture. This high velocity inclusion, This is RTH velocity imaging for this part. Ultra high resolution velocity and logs. This is 2.5 meter resolution per depth. High velocity, red, blue, low velocity. This zoom. Zoom in comparison with the resolution of well-log data. This is example of velocity cube, cross-section and depth section. Cross-section, depth section. And diffraction cube. Cross-section, depth section. 200 square kilometer. Voxel size about 50 per 50 or 10 meter at the depth. More than 100 attributes. This example concerns the high applies to the horizontal drilling, assisting horizontal drilling. The red layer is the target horizon sandstone with the oil. In our attributes, it's our one attributes. Red color is target horizon. Cross section is 10 kilometer per 2 kilometer. This is using of this information for real assistant for precision drilling. We predict the point of the predicted entrance in the target horizon, and our prediction accuracy not more about 2 meter, 1 meter about target horizon is real data after our prediction. This is the result of our prediction of amplitude prediction for fraction.
Again, Professor, can you just go back a slide here? If you just go to the previous one, the red is a sandstone, your target reservoir. Over here, which is your target reservoir, the magenta or the red one?
Magenta is the target horizon, yeah.
Okay, okay.
Thickness about 20 meter more, maybe to this 30 meter, this 20, this 10 meter, yeah.
Okay. Okay, excellent.
Purpose
Thank you.
To point to show the point of entrance for horizontal drilling.
Yes. Okay. Let's go ahead, sir.
This is real example of our prediction fracturing based on of our attribute so-called diffraction attribute, and this real tidal oil, green tidal oil, 23 kilometer. Red is the basement. So our purpose to show what point for only for all tidal oil, green. We calculate and show that this is which point is perfect. This point is concerning the natural fracture in the basement. Is tidal oil. And the oil flow rate about 20 cubic per meter per day. But at the upper part of basement, there is huge fracturing diffractivity zone. And after our prediction, they drilling and obtained oil flow about 150 cubic. This point. In the upper fracture and upper of basement. This is an example of our using our RTH attribute in structural mapping. At the left, our RTH mapping. At the right, PSDM maps. Our error concerning the incrementary about 2 meter. Voxel size 2 meter per depth. This is using our RTH attribute for the thickness mapping. Red color about 20 4 meter thickness, blue about 80 meter. And this is predict of the velocity concerning the for the sweet spot purpose. The blue is the sweet spot because it concerns the porosity, velocity porosity, and multiple more than 20 times excess of accumulation gains, the production over neighborhoods about one year. During 1 year, 1.5 year, the production 20 times more than in this two horizontal wells. So if we know one sweet spot, it's enough to drill one well, horizontal well. It's enough. The next example concerning the depth.
Sorry to hold you back again. Can you just go back one slide? I have a question. I believe on the left and the right are the same map. I mean, the same area and all. But one is a thickness map, another is your velocity map, meters per second. But somehow the thickness map and the velocity map, I do not find much correspondence. Can you please explain this?
Yeah, absolutely. Not correlation because is a depth. Is a smaller depth, there exists huge porosity, huge deposit of the gas. It's conflict with no correlation, but it's a real example. Yeah.
Okay.
The next 4 slides concerning the depth of possibility of depth of the depth of our velocity prediction. We have the two orthogonal profile AABB. This is depth section concerning AA through the point O. This depth about 12 kilometer, distance 28 kilometer. Red color is the object with a small velocity because it's slowness. Red color is low velocity, and gray is a high velocity. 12 kilometer with a detail 25 per 5 meter. 5 meter per depth. Is about 40 million pixel. In this case, pixel 2D. So in the depth of the 10 kilometer, we can see the low object, velocity object. Yeah, very interesting because it's a high velocity, gray. But suddenly we obtain at the 10 kilometer huge object with a low velocity. Yeah. Oh, this is orthogonal B section. This is A. This is B section. Orthogonal. So with this depth, we can see the similar low velocity object. At more than 10 kilometer, with a precise 25 per 5 meter. And then interesting what is will be pictured at the for example at the right to voxel at the line one, and then this point with line 2. How it coincide? This is line of two profile. Line 2, line 1, line 2. Perfect coincide, perfect with a precision of 5 meters from 0 to 12 kilometer. It's perfect coincide. This is left. Is similar. velocity. The structure, we can see the structure, the default, and many bigger object and some other. It's very informative. Our RTH attributes we then use as input data for the quantitative RTH-based prediction roadmap. We use input data. This is out data which we can see before, and we use the one attribute and merge with the well testing and logging data. Testing and logging data. Testing and logging data. And this is the next part of our prediction is using RTH cube well testing data. The output of this RTH driven machine learning prediction, cubes of quantitative RTH prediction of porosity, permeability, on flow of drilling accidents, gas, oil, brine, water, and absorption thickness, letter type prediction, etc. For each by which voxel is the result for the prediction cube of brine, prediction cube of gamma ray, and so on. More detail. It's a last slide concerning with some detail of machine learning. Machine learning, we use well testing and logging data, use machine learning merge scheme, which with the result of this idea is as much as possible voxels need, as much as minimal of it's need of minimal minimization of or quantity of the attributes. And example case study. This is one attribute very informative arrival time discrepancy concerning the velocity, and we merge with three well log data. 600 square kilometer. We use three well for machine learning. Only 3 wells. It's a huge section. Is a huge square. And this is the result of prediction. We learning and predict, which is very nice. Coincide with the real well logging data. Yeah, this is 26. 26. 26. We use full blind test for all welling. So this is another case concerning velocity prediction by RTH and well logging data. Is a cube of the velocity in comparison of the velocity with the well logging. The differ 200 square kilometer. This interesting. We predict some, for example, porosity, permeability, and other parameter. Use only horizontal well log data. Is square about more than 100 square kilometer, but very thin layer about 23 meter. Red color. Low is a green clay. Sandstone 1 without gas. Sandstone 2 red is with the gas. In where is this small, very thin layer? We have used 9 well logging data concerning the porosity in this case, and our machine learning we predict the porosity with the blind test data, green in the all section, all layer, all red layer, more than 100 square kilometer. So we use 18 RTH attribute. This is the result of the all inflow rate prediction by RTH and well logging data. If we we have some information about the oil flow. For example, in our 1, 2, 3, 5 wells, and we use for 14 attributes and learning and predict oil flow in cubic meter per day. Cubic meter per day. Red, more than 10 cubic meter per day. Blue, 1 cubic per day. Predict in all voxel, dimension voxel, size voxel about 25 for 5 meter. In each voxel we predict the oil flow rate. This section, 2 sections. This absorption prediction cook by RTH well login data in each voxel, which size 50, 10 meter. We predict absorption, and in each voxel in meter. It's quantitative prediction in which voxel we predict the absorption in meter. This absorption thickness of structure map, for example. This is 3 type of the predicted value: absorption, brine, and gas production. So each voxel will predict for example, gas in meter. For example, each voxel with this voxel, we predict meter. Then for example, we want to know what is the thickness of predicted gas in this layer, product layer. Product layer about thickness about 50 meter, and thickness of predicted is this layer, summation layer. This layer, summation layer, is about example about 25 meter is red, but is red no, about 10 meter, 10, no more 10 meter. I guess we predict is this layer. For example.
Professor, okay, now one question. You said absorption. I think I missed it. What do you mean by absorption? Absorption of the sound of the elastic wave, or?
No. Absorption, which information from well.
Okay, what is that? What absorption signify?
Absorption is how much in meter we can see the absorption for drilling, for example. 10 meter absorption is information not as I said logging, but it's information but testing. It's testing information, not logging. This is logging information, but in this case is absorption is testing pure absorption, testing for brine, and testing for gas. Testing we can to measure from wells how much in meter is this voxel, how much absorption in well, and after that we use this information for learning with our attributes and predict absorption in each voxel, this voxel 50, 10 on this cube. And this example of the thickness of predicted absorption of brine in layer, in product layer. This product layer, for example, this product layer. The last drilling accident prediction by RTH and well testing data. It's very interesting because we have information testing of only in one well where accident. There exists 3 accident happened, 1, 2, 3, and use some number of RTH attributes 63. We can predict and we can learning and predict the zone of higher accident, possible accident, higher, average, low.
By accident, you mean lost circulation?
For drilling, during the drilling, only during the drilling.
Are you talking about the lost circulation? I mean, when you drill a formation that is heavily fractured, the drilling fluid gets lost into the formation, and the loss can be very severe. It can be 100%, normally described as percentage. So whenever we try to, besides the shallow gas accidents or blow-ups, we normally are very careful about loss circulation, because loss circulation enhances the cost of drilling, rather aggravates the cost of drilling, as well as there's a downtime. And so we normally we associate fractures with the loss circulation. So when we're talking about the drilling accidents, are you meaning the drilling loss circulation? That is my question, sir.
Lost circulation. Lost circulation is accident. It's stop the drill. This one happens, second happens, three happens, three accident in during the one during the well. No, it's stop it, three stop it.
Oh, okay, sir. Thank you.
It's latotype prediction using the information of the latotype prediction of the well. And the last before is our GeoMax2 product lines, RTM imaging concerning the RTH velocity and more than 100 attribute, which is possible to use for the processing and interpretation. And the second more powerful is to use all of these attributes and use well-logged data for machine learning and prediction oil flow, porosity, permeability, and so on. Yeah, technology readiness is our team, our paper. Our team, more than 15 specialists with 40 years experience. We use RTH technology testing of the 27 oil and gas fields. Infrastructure, we install a company GeoMax technology installs the very high, especially designed for this RTH approach cluster, especially design. About 1 petaflop with energy design, 1 petabyte then. Especially design is including the special software, about 500 source code. And okay, in conclusion, RTH using a combined advanced seismic exploration, artificial intelligence, and high performance computing, opening new horizons of hydrocarbon exploration and development. First, its implementation will significantly improve oil and gas industry efficiently, delivering accurate prediction, process optimization, and substantial increases in hydrocarbon production. RTH is not evaluation; it is a paradigm shift from scalar to vector imaging, scalar and vector, from amplitude to amplitude and phase. From iterative to direct inversion, and from low resolution to AI-ready matter scale subsurface intelligence. RTH time-dependent full scattering seismic exploration is the new paradigm of exploration of the 21st century. Second, yeah, I finished. Okay.